So welcome everybody to my talk about uncovering hidden bugs and vulnerabilities in C and C++. I'm happy to give it today, and like I said, welcome everyone. A few words about myself. For the beginning, my name is Jochen. I'm a senior software developer here at Code Intelligence. I have a master in computer science. My background is mostly from the backend and web development side. And I have a strong focus on software quality. Like, it was always part of my interests. And this is how I ended at Code Intelligence. At Code Intelligence, I'm responsible for developing the CLI tools, or the CLI tool, which we want to see today. So our today's topics are like an introduction into fuzzing, so everyone is on the same page. We know what we are talking about, some basics, keeping it short. And then I will talk briefly about our tool, our CLI tool. We call it CI Fuzz CLI, and what it can do for you to get easy access to fuzzing. And then I will demonstrate it. The commands we have and how it works, and setting up a project and finding our first bugs and vulnerabilities maybe. So what is fuzzing and why should we fuzz? Why it's pretty popular recently, and a lot of bugs were found with it. These are some recent numbers. Google is big in the fuzzing business, I would say. Like, they have Google Chrome Fuzz. They have a project called oss-security where they fuzz popular open source projects regularly, and they have big numbers of bugs and vulnerabilities found. Mozilla is also fuzzing, Microsoft, Linux, all the big players are doing it. And beside the number, there are already not only a lot of bugs, also severe bugs. For example, you can find Heartbleed easily with fuzzing. It wasn't found with this, but it's easy. For example, Shellshock and Bashdoor, a lot of the vulnerabilities included in that were actually found by fuzzing. And there was a research project, and where they fuzzed Adobe Reader for 50 days and found 50 CVEs. So I think these numbers are pretty telling how much you can achieve when using fuzzing. So what is fuzzing? It's a term, I would say, established around the 90s, 89 to 90. Was it first coming up under these names? Actually, the idea is way older. The basic idea is putting your system under test, with feeding it with random inputs and see how it crashes. And the idea is pretty old, as I said, and what it makes it different recently, or what makes it more appealing to just put random inputs, is the improvement that were made in the recent years. And this is called coverage-guided mutation-based fuzzing, where the idea is that you don't just create random inputs without knowledge about the application and everything. It's like you see how the application behaves under test with specific inputs, and then you generate new inputs based on this information. For example, that can be simple bit flipping. It can also genetic algorithms to have more specific things going on. And the very important thing here is that you choose the inputs or select the inputs and mutate them based on what you see in the application. So the big step is that actually you watch the application. This can be with coverage instrumentation, that you collect coverage information during your fuzzing runs, or it can be that you hook into some operators and see how that behaves, or if there are like some magic strings or numbers used, and if this is like giving you more insight into the application. So another picture to make it a little bit more visual, what changed. On the left side, the black box is how fuzzing was done before. Basically, you generate a lot of inputs and hopefully you find a bug or vulnerability, but you don't have any knowledge about the inner structure of the application under test or the system under test. And of course, it will result in a bug maybe or in a crash, and you have some insights about these bugs, but it's really not like you know what's going on in the application, or the fuzzer doesn't know what's going on in the application. And the more modern approach with coverage-guided fuzzing is that you like have insights in the system under test, and that you can mutate, or the fuzzer can mutate the inputs accordingly to this knowledge. And you can compare it to a maze where you have like a map or a rough idea how it goes. And then it's more likely that you find not all, but maybe way more bugs or vulnerabilities than with a black box approach. How this looks in like a modern fuzzing system will this chart explain. We have in the middle, we have the fuzzer. It's the main driver of this whole system. It mutates the inputs and feeds it to the application. And on the right side, we have the system under test. And it's important for the modern approach that it's instrumented. We have usually it's called fuzz target or fuzz test. This is a function that receive the mutated inputs from the fuzzer and then call your code under test or your application under test. You can it's the same way you would do it in a unit test. Like you call your function with inputs. The difference is that these inputs are way more, and they are mutated. They are based on insights gathering the fuzzing run. And this is why you also, it's recommended to have the source code for the instrumentation or for insights. So what comes out of the system under test that's instrumented is the coverage data, and like I mentioned, also stuff that you gathered with hooks like compares or magic radius. And this is feeded back to the fuzzer that then decides how to continue the mutation. For example, if there's an input that is interesting because it's covered new, or it's make new paths through the application available to the fuzzer, then it's an interesting input. And the fuzzer will save it in the generated corpus. This is what we see on the left side. And also when the fuzzer starts, it uses inputs that were saved in the generated corpus. And also in the seed corpus. So if you want to give your fuzzer some hints how specific data should look like, for example, if you have complex data structures or data that has to be in a specific format, that can be like an image format or like your data structures, then it might be helpful for the fuzzer giving hints in the seed corpus. And this is what you can do there. And of course, at some point when the system under test crashes, the fuzzer will give you the crashing input. So you can use it to reproduce the crash. Yeah, this is like the basic components. And like I mentioned, it's really like the important thing is that we gather information from the system under test to really see which inputs are valuable inputs, the ones that end in the generated corpus. And yeah, so far for like the components of a modern fuzzing system. And what the fuzzer does is he offers ways through your application, like to all the switch statements and loops and everything. Like he tries to find, with help of the coverage instrumentation, like a way through your application. But to really trigger a bug or a vulnerability, you have to use sanitizers. And here are like 4 very common C++ sanitizers, like the address sanitizer, memory sanitizer, undefined behavior sanitizer, or threat sanitizer. In general, you can use them even without fuzzing, but if you imagine that you have them with fuzzing and the application finds a way to reach code that is triggered by the address sanitizer, for example, it's way more valuable here. And we can take a little look at the how the address sanitizer works, for example. The idea here is that that it replaces the malloc and the free function of your library and of your standard library, and makes some, it's called poisoned areas around the memory you want to allocate. So, for example, if your application at some point try to access the red areas in your system memory, then the address sanitizer will like throw an exception of like a failure, an error actually. These sanitizer usually slows down your application, sometimes significantly. So this is a reason why you wouldn't use them like in a normal scenario, but for fuzzing, where it's the goal to find these kind of bugs, and we will see later on what kind of bugs you can actually find with a different sanitizer. It's something you should do, and they really like super optimized. Like the async sanitizer, there's a lot of work went into the overwritten functions to make that really performant. But it's still, I think, for the async sanitizer, it slows down by half. So yeah, and the next slide we will take a look what kind of errors you can find. On the left side we have all the sanitizers, like the address sanitizer. It's usually good for finding different type of overflows or use after return free scope errors, or in general memory leaks. The memory sanitizer finds use or like reads from initialized memory. The threat sanitizer is good for like data races, deadlocks, this kind of stuff. And UBSAN usually finds the undefined behavior things that can be out of bounds with arrays and bit shifts, stuff also your compiler can find, but a little bit more, going into the deep. Yeah, and then on this side, you have like the stuff you find with sanitizers. On the right side, we have these stuff that is like plain crashers. Like maybe your fuzzer finds something that is not triggered by the address sanitizer or a sanitizer in general, but it's like really a plain crash where your application would have crashed. This can be fine. Then there's also detection for like infinite loops, when the application slows down, when into timeouts, when memory get exhausted. Stuff like this can also be found easily, or way better with fuzzers. And you can check for logical bugs even. There's things like differential fuzzing, where you have maybe 2 implementations of the same protocol and you want to check if they always behave the same. You can use fuzzer for this, or you can do stuff where you have usually like round trips, like uncompress, decompress, or compress, uncompress, or like if you have like cryptography or like encoding, decoding, stuff like that, you can also cover very good with fuzzers. And this leads to the next points where you see what are usually good applications or libraries you can that are good targets for fuzzing anything. So in general, everything that consumes untrusted data, or rather complicated data. So classic examples are like parser or media codecs, protocols in general, a lot of crypto stuff, compressing, like I mentioned before, but even like stuff like compilers, browsers, databases, all these stuff that is has to handle like complicated input, or as I mentioned, untrusted input. These are very good use cases for fuzzing. So these were like the basics of fuzzing. If there are any questions, I can answer them later. So what is our goal with CI Fuzz, the tool we are actively developing here at Code Intelligence? Usually fuzzing requires a lot of setup and knowledge about how to use these fuzzers, and it's not super convenient to get started there. And the goal with CI Fuzz is to make it easier for you. And in the end goal, it should be as easy as writing unit tests. Everyone, or most of you, should like be familiar with writing unit tests. And our goal is to provide this experience with CLI Fuzz, with our CLI tool, CI Fuzz. So, and it should be like doing that for a variety of build systems and languages. So currently we are supporting C, C++ with our CMake integration, which I will talk on the next slide about it. We have IDE integrations based on the CMake integration for C-Line and VS Code, but the chances are high if you're using an IDE that has a CMake integration that our stuff will also work. Then CI Fuzz by now supports coverage reporting. You can see which path or how much of your application was actually covered during a fuzzing run. We have sandboxing under Linux based on Minijail. We have regression testing already implemented and the management of findings. What is coming soon is support for Java. We have our own Java fuzzer, or fuzzer for the JVM. It's called Jazzer. It's also open source. You can watch it in our GitHub repositories. So this support is coming soon. We are already working on it. And then we have like our own JavaScript fuzzer called Jazzer.js. It's also open source, released recently, I think like a few weeks ago. This will also get included into CI Fuzz. And then stuff like out-of-the-box debugging or the connection to our SaaS solution, if you want to like doing continuously fuzzing your applications inside your CI/CD pipelines. This is also coming soon in CI Fuzz. So today we will focus a little bit on the CMake integration parts, but just for you, good to know is that we have also ways to Fuzz C++ project without CMake. We are supporting other build systems by providing a build script that you can use. There's a little bit more manual steps necessary than with using our CMake integration. Yeah, this is the current state. So our CMake integration manages all the compiler and linker flags you have to use for fuzzing and coverage instrumentation. So this is what I mean with making it easy for you. It also integrates with C-test as regression tests. So a little bit background on this stuff. If, for example, and we will take a look later also, but for example, if your fuzzer finds an input that generates an error, you have the possibility to add it to our seed corpus and use it as a regression test. Like, for example, similar to the you would use it in unit testing. So you have an input that generates a specific error, and you don't have to use it with the complete fuzzing run that takes longer, it's way more effort for your machine, for example. You just can use this single input, run it through the fuzz target, and get a result. And this is what we do with question tests. Like, if you have a finding, you can easily reproduce it, and you can easily check if it's a question or not. Then also the CMake integration handles the different build directories. For example, the fuzzing coverage and question tests get built in separate directories. And with the CMake underlaying, the CMake integration underlaying, you get like good support in your IDEs. We will take a look at C-Line and VS Code later on, so we have an idea how this can integrate in your daily developer workflow. So now it's time for the demo. I have prepared one example from our repository. You can also take a look later and try to play it through on your own. The first thing is that we have to install CI Fuzz. I'm just removing my previous installation, so we have the full complete progress here. We provide a pretty easy way in our GitHub repository to install it. You of course can install it from the source, building it on your own, but you can also use our install script we provide. Oops, one moment. This is where we want to go. So in the README, you find this section that provides an easy way to just install it. So we wait, the installer is downloaded. It's choosing the right installer for your operation system. By now we are supporting Linux, Mac OS X with the no matter if you're using an M1 or like an Apple Silicon-based Mac or an older one, and Windows is also supported. So this is the installation is successful. Now you have to add the installation location to your path. I already done this. So now I have my CI Fuzz command available in the recent version. The next step is I prepared like a directory where we find a simple CMake-based project. We can take a look at it. It's really simple. We have a CMake list, we have a main application file, and we have some stuff that is included. We can now take a closer look at it. So this is the application we want to explore with our fuzzing. It's a little bit simplified, so we can actually see what's going on. So we have multiple branches that are reached under different conditions. And then we have here like a undefined behavior that we have a bit shift that is larger than the size of the type. This is something your compiler will also notice in general, but to trigger the undefined behavior sanitizer, we use this case. And then in this last branch, we have like a heap buffer overflow. And our goal is in this little demo to write a fuzz test that actually trigger both of these bugs. So currently, our main application is just calling the explore me function, and our CMake list file looks like this. So what do we have to do? So the first step is to initialize the project. You can do it by CI Fuzz init, and then we will show you the next steps necessary. So in this case, we have to include our CMake package and enable fuzz testing. This is stuff that were installed by the installer we saw before. So we enable fuzz testing. And what this step also does is it creates a CI Fuzz YAML. This is our configuration file. For example, you can turn off notifications here. You can use specialized arguments for the fuzzer if you are a more advanced user, for example. Or you can just turn off the sandbox, or you can configure your build system, or like I mentioned before, if you have like not CMake using, you can also provide a build command here. This is all done in the CI Fuzz YAML. So the next step is now basically we have enabled fuzz testing. We can verify it with just doing a simple build. Oops. Like this. So everything went through. We can also run the make based on it. No errors found so long. So the next step is to actually create the fuzz test, and we provide this with the command CI Fuzz create. And by now you are only asked for C, C++, but as I mentioned, in the future we will provide more languages to fuzz here. So this creates a test stub, like a simple file that needs everything to be you need for fuzzing, and it provides information on how to actually include it into your CMake. So we do this, and it's work similar to the add executable command you might know from CMake. So you have a name of the test, and you define the source files. And to start the fuzzing run, it would actually work already. So we can take a look at the file that was generated. It's like these, and it looks very similar for if you're used to unit tests. We have like a test setup method where you can do stuff before the fuzz test runs, and then you have like your main corpus and the main fuzz target function. And here you see the fuzzer will feed an array of bytes. It's just like that in a specific size that can vary a lot, and it can be null size, it can be super big, depending on your data and depending on what the fuzzer actually explores in your application. And now to run this test, you can just reference it by its name, and it will start. It will compile, and then it starts fuzzing. And the thing is, here we're actually doing nothing. So it will, like, the application is not tested by now, but you can already see that the fuzzing is running with more than 1 million executions per second. And yeah, so this is basically what you need to do to get your fuzzing setup done. And now we want to write like an actually fuzz test. Like we want to test our explore me function. So what we have to do is a recommended step is using the fuzz data provider. It helps you a lot for casting the byte array, the byte buffer, to something you can actually use. So in our case, we need a data provider. We call it fuzz data, and we initialize it with data and size. So if we take a look at our explore me function, it takes 3 params, 2 integers, a and b, and a string c. So this is what we need. We need an int, and we take it from fuzz data, and it offers easy functions to get like the different data types. So we want an int here. And then we need the same for b. And then we need a string c, and we can get it from the fuzz data provider too by consume remaining bytes. This means everything the fuzzer generates beyond the 2 integers is used as a string in the array. And now we can actually call our function. So we need the include here. And this is basically all we need. So if we now start the fuzzing run again, I made a mistake. So just like you need the linked libraries for the executable, you also need it for your fuzz test. And one way to do it in CMake is like this. So, but if you're familiar with CMake, this should be no surprise for you. Another mistake. Let me use my other, okay, my path was a little bit wrong here, like this. So, and now you should see like immediately is like super quick. It only takes a second or less for the CI Fuzz to find these bugs. And if we take a closer look, it finds 2 bugs. It finds the undefined behavior, and it finds these heap buffer overflow. It tells you where, in which line, and which column. It took like 1 second, and we have like 13 new seeds on that. Yes. So the what we now can do is taking a look at the findings. We provide a command that is called fuzzing, finding, and it lists them all, you're finding in the code, and then you can, for example, take a closer look to them. Here we have the undefined behavior. It really like prints you the stack trace, the specific error, where it happened. And the same thing is possible for the, of course, for the heap buffer overflow. And here you get like even more information because the address sanitizer provides you detailed information about the where the error happened in memory and what was like going on there if you need more advanced debugging. And you can see like the question input that produced it. Then one thing you can do from here, these are the basic steps you have to perform to get actually a fuzz test running on your machine. Usually, if you started with your application, you will have like really soon the first findings, but sometimes it can take a while. Like this is an example. This is why it only took like a second to find. But there are deeper hidden bugs and vulnerabilities where you actually need to run it like hours or days on constant fuzzing, depending on your application and the data and everything. So this is why we recommended executing it also in your CI/CD pipelines. So the next thing you can do from here is that you watch the coverage report, like that you take a look which of your code was covered. For example, also with naming the fuzz test. And we support different formats. Like you can do it in alcaf or HTML, whatever you want. Like this. And then it will like make the build with the coverage instrumentation. It will provide these, I will zoom in a little bit, this HTML report in our rather simple example, which lines were touched and how often, and it will show you how the fuzzer reached it. Like you can see, basically it runs 15 times. It took him 15 times to get over this branch, then 7 to get over this, 3 to get over this, and then at the end, with the last one, it got into this branch and triggered the heap buffer overflow. We have also like a report on the CLI that summarized it from which file, how many lines were covered, how many functions were covered, and how many of the branches were covered. This also it's always based on the your included code, not the whole application. If you include the whole application and it's covered, then maybe. But this is basically our code that was included in the or linked in the fuzz test. So, and like I mentioned, you can do it as an HTML report or archive report. And then the next thing I want to show is how you can integrate it in your IDEs or in your development workflow. We also provide a command for that. It's called CI Fuzz integrate, and then it provides by now multiple integrations for CMake in general, for Git, because we create a few folders that you might want to be in your Git ignore, and a VS Code. We can do them all in this case. And then it will print you like the next steps. It says that it's create a task JSON for VS Code. This is what VS Code needs. It recommends you an extension to use for your coverage stuff. It has links how to use it in CLI and in JetBrains IDEs. Yeah. And if we take a closer look here, it's created a VS Code folder and added like task JSON if it's not existing already. And it adds our CMake user presets. We will take a closer look at them soon. So how does the IDE integration looks like? We have integration for VS Code. Oops. I hope this is readable. I will try to zoom in a little bit. Here we have it. So this is the same project we worked on, and now you can see we have like the different build types provided by the user presets. So you can do a coverage run, or you can do if you select here, you can actually do a regression test that I mentioned before. You can build it easily, and then you can also run it. And what we also provide is an easy way to view the coverage of your test. So if this is our fuzz test we wrote before, and now we can say we want to run a task, and it's called coverage, CI Fuzz coverage from the current test. So it knows which test is used here. Oh, this is an unexpected error, to be honest. I will take. Okay, one moment, please. I think there were some environments variables missing. So we can use it here, task, same task again. It does the coverage build. It's created an alcaf report, and the extension I mentioned before that we recommend, like coverage gathers, now helps you to see the coverage. You can activate it here. It's also like the way the extension provides. You now see the code that is covered, and if you take a look at our target, and also let it put here, you can see which lines were covered by your test. It provides an easy way to get through the application, to your application, and see what code was covered by the fuzz test. And beside the VS Code extension, we also, besides the VS Code integration, we also provide a way for CLI. Everything is based here on the integrations of the CMake, based on the CMake integration. Wait a moment, I will try to zoom here too. Here we have it. So in C-Line, we were able to have a little bit deeper integration. You can actually run this fuzz test as a regression test by clicking this play button. You might be familiar with it from your regression tests. And you see here, it's runs through, shows you the outputs and the path covered. This is the output from the Explore Me. What you also can do here, all based on the little play button, is that you can run the coverage run here. We provide a way to integrate it in C-Line as well. So you see the whole fuzz test is covered, and of course our Explore Me CPP file is also covered completely. And then here you can also start debugging. So if we want to have a breakpoint here, for example, you can just run it with the play button, and then you actually have your runner going. And you can see it's using the inputs from the seed corpus, from the findings before. So some values here that might be generated from a previous fuzzing run for the finding. So this is basically our IDE integration. Like I mentioned, if you're using another IDE that is also supporting CMake, the chances are high that you can use the presets we provide and do all the stuff you are used from CMake here too. So this was it basically from our example project. If you have like real life project, it's not completely different. For example, we provide also these demo projects with a current state where we had find vulnerabilities and bugs in our repositories. And the stuff that was done here to, for example, DINT is a barcode parser to provide a fuzz test here. It's the same. Like it's you get your data input in your fuzz target, you feed it into the application on the test. And the CMake stuff is similar. We have these CMake list here. And you see, we add a fuzz test with the function provided by our CMake integration. We link SYNT into it. We give some include directories, and it's basically working. So with an existing project that already have these like libraries, like here, SYNT already had a CMake target building this library. It's super easy to make sure that everything gets linked correctly, and it's easy to start from here. So this was it for the live demo. Some closing words about some tips for the start. If you actually want to get started with fuzzing and using our tool, then I want to provide you some good starting points or things you should have in mind when starting writing your first fuzz tests. So one thing is try to optimize for coverage, because the idea is that the fuzzer is able to explore your application, like making different parts to your code. And there can be scenarios where it's like hard for the fuzzer to come up with the specific data structure it needed or with the specific magic values that you compare at some point. So if there's a way to provide it to your fuzzer with the seed corpus, do it. It helps a lot. And then another important thing is that your fuzz test, and the same is also true for your application, should be deterministic, stable, fast, and with not wasting a lot of resources. The thing is, to be effective for fuzzing, it needs a lot of runs. Like you saw, we had executions per second that should be multiple thousand times per second. And to achieve this, it's important that you're not wasting resources. So try to minimize the file system access, try to minimize requests going out, try to be having it deterministic, meaning that you're not having a state. Every fuzz run or every input should be starting with a new state. If it's not possible for your application, there are ways to manage this a little bit more. I guess we have in our blog, we provide some information about this. Yeah, and then what we did in the example, use the fuzz data provider to make sure that you have consume the right types and everything. And yeah, these are tips to get started. Beside that, feel free to reach out. Our repository is open for contributions, for issues. If you have feedback, question, really feel free to reach out to us. We will be happy to help you. And with that, I'm finished with my talk.